So yeah, we know why things break, we understand it, we even know what to do about them. The trouble is we're not doing that. We're allowing our stresses to arise and not control the stresses. Because the stresses are there, they eventually will lead to a breakdown. So what is the opposite of that? What is the prevention of stress and of failure? Well, the opposite of that is reliability. We want to actually create reliability on purpose. I've got to understand why things break so I can then work out how to not break them. And that will then create the reliability that we're actually looking for. So reliability has a number of definitions. There's a very formal one, the one that is used by reliability engineers, and that's the top one there. Reliability is probability that an item of plant will perform its duty without failure over a designed time. That's the one that is quoted in the books, and it talks about a number of things. One is probability. What is the chance? What are the odds that it will do its duty without a problem for the required time? Another definition I've come across is the military definition, the chance of completing the mission successfully. And one that I'd like to use is the one that talks about the chance of success. What is the chance of success of this item, of this process, of this task? Because reliability is high chance of success, high reliability, low chance of success, low reliability. So we get reliability by creating and building a thing that can do the duty, preventing its failure. So designing reliability is a big factor, and then preventing its failure is the second factor. So these two vehicles here, if I was to put that vehicle in that situation, wouldn't have a hope. Isn't designed for the job. If I take that vehicle into that situation, it'll probably complete the circuit. It'll just never win the race. So making the right choice at the beginning is vital. If I make the wrong choice for that situation, no matter what I do as an engineer, no matter how perfect that machine is, if that machine is in the wrong place, it cannot survive. So now I have to go back to the beginning of the life cycle and ask my guys who select the machines, what is your thinking in your selection? Why have you chosen that design for this situation? What makes you think this thing can do that job? Because if you've chosen the wrong machine, the wrong parts, the wrong design, the wrong materials, it's not going to make it. Impossible. No matter how hard I work after I get this in my plant. So that's why the life cycle concept is so vital. If I get it wrong at the very beginning, then no matter what happens in the coming years, I cannot do any better than what the design allows me to do. So that early day choice, that first day choice, everything else hangs off that. And if the wrong machine is chosen for that job, it will always be a problem. So if the chance of success is low from the beginning, then I will always have poor reliability. We know why machines fail. Things like defective parts, poor assembly, manufacturing errors, operating overload, aging of parts that are aging but not replaced, local environment degradation. This is an example of our lubricant. If our lubricant gets water in it, the local environment degrades. If it gets wear particles or dust and dirt, the oil is degraded. And of course, eventually things do age. I'm 57 now, I'm getting tired, my muscles aren't as strong. As the years go by, my hips and my knees are going to cause problems. I'm expecting that because it's going to happen with time. Things will age. What we've found, there's a proportion of parts failures. A lot of our parts fail very early in their service life. Between 50% and 70% fail in this early life failure zone. I define that as a failure from some sort of error. Now, this is a brand new part and it fails. A brand new part fails. Well, it can only fail for one reason. It's been stressed very, very high, very, very early in its life. From our fatigue curve, it must have been stressed hugely very early on. This zone here, this flat zone, is the random failure zone, and this means a situation arises that the stress is induced by some sort of creation. Don't know what that is. There is a reason for it, but that creation and that stress is a random phenomenon. It'll happen at various times. So there will be, across the whole life of a machine, some sort of failures that occur from time to time. Then, of course, as it gets older, our parts will fail. So yeah, we understand why they break, understand what causes them to do that. The challenge is now is to prevent that. Now this big curve here, this main curve, is called the rate of occurrence of failure. This is the curve for a machine. This one that's a wobbly line is a single machine. And a single machine, it fails when its parts fail. So this particular wobbly curve here would be a machine. As each part fails, the machine failure rate increases. Here, the failure rate is very, very low. Here it's high. So the higher the failure rate, the more parts that are failing. When I get many of the same machines together, a huge group of those machines, maybe 1,000 of them, we get an average figure. So this dark, thick curve is the average figure of many machines of that same model. What this is trying to say is that my machine fails because the parts fail. If I can prevent the parts from failing, then this curve comes lower and lower and lower, because that curve is a result after the parts break. All right, this slide here is to help us understand where those curves come from and to talk a little bit about what reliability actually is and what it looks like when we have reliability. So just going to take an example of a glass and talk about how reliable is a glass. What is the chance the glass will hold water next time we want to use it? How many guys have broken a glass? Have you broken a glass over your life? Yes, it happens. That's just one of those things you expect every now and again. Randomly, there'll be a broken glass. When you look at why they break, there's a number of reasons. And I've put 15 down there. Slip out of your hand, they fall off a tray, they're on the edge of a table, they get knocked. There's a whole bunch of reasons that glasses break. So if we can look at what happens with the life of a glass, and we can just see what the impact is then of the reliability of a glass. What I've got here is a situation we have glasses from around the world. We'll just say the manufacturer of the glass made 1 million glasses. 1 million glasses, and they're in 12 packs. So I go to the store and I buy a pack of 12, which means there's 83,333 households with glasses, with a pack of 12 glasses. Now, in my house, when it comes to breakages a year of a glass, we break about two a year. In your place, you've got young kids, have you?
Grandkids.
Grandkids, okay. Any idea of what an average breakage of glasses in your place would be?
Greater than 2.
Greater than 2, yeah. And yourself, Bruce, with
Just only 2 of us, so we hardly ever break a glass.
Yeah. So it depends on the situation. Depends upon the families and how many kids, how many opportunities there are for these things to break. So I'll take the figure 2 because that's sort of a reasonable number to work with. So we can say in these 83,000 households, about 2 a year. So 167,000, what's that, 667 per year would break around the world. So I can then take that information into a plot. And if I just say, let's just break this into 6-month periods, 12 months, 24, 36, 48. There's a few things we can say about this situation. On day 0, the very first day that people get their pack of 12 and bring it back to the house, there's going to be, they're going to take them out of the pack, they're going to put these onto a shelf in their household. From your experience with breaking glasses, do you think out of these 83,000 households, some of those will break that glass at the very first time they pick it up, go to stack it in the shelf? So our failure rate at the beginning will not be 0, it'll be some number above 0. I've got no idea what that number will be. I'd have to survey all these households and ask them, but I'm guessing 100, 200 around the world would break. Now, after 6 months, we're going to be using the glasses. There's going to be friends visiting, there's going to be the kids coming across, the neighbours' kids come over for drinks, we've got birthday parties. Things begin to happen that use the glass. So that failure rate, because they are now being used, is going to be happening. Things are going to start breaking. And as the year goes by, again, more opportunities. There'll be Christmas, there'll be New Year's, more festive seasons happening. You're going to find that then, of course, the years begin to repeat. And year after year, similar sorts of things happen. Occasionally you're going to have the big party, the 30th anniversary, 25th wedding anniversary, those sort of things occasionally going to happen. So you're going to find that the curve over time begins to level out, because the opportunities just keep repeating. And as I say, about 2 glasses a year on average break in my household. So what we can say from a family of 1 million, if we divide this figure here by our million, we get 0.167 is the average failure rate of our glasses across this population around the world. So this line here now becomes that particular value there. And the assumption is that it's continuous. That line will be pretty much the same, at least in my household, forevermore, because the opportunities keep repeating and 2 a year on average tend to happen. Once I've got an equation for that line, I have now got a way of projecting the future. So I can say between years 2 and 3, if every household across the world that has these glasses had an average of 2, then every year I need to replace them with about that many glasses every year across the world. So the manufacturer of these glasses will know he's going to make that many glasses a year to replace. In my place, so when it comes to stocking those, I can say, well, every year I've got to buy 2 more of these to replace the ones I'm going to break in the coming year. So I can now develop a stocking policy, a resupply policy. I can work out roughly how many glasses is going to break in the coming 4 or 5 years, what that will cost, projecting it forward, because I've got a stable failure rate of those glasses. So from this information, I've got a curve representing the history of the glass. That will be the same as the future, assuming nothing changes. So I've now got an equation to predict the future. And reliability engineers, that's their job, to give us equations of the parts we use and when they fail to predict the future of these parts. Very powerful logic, very powerful stuff. For a maintenance guy, having an equation of the future failures, fantastic. You can begin looking at strategies, procurement, sparing, dealing with subcontractors when to bring people on site, when to begin maintaining machinery. So very powerful technique. So I'm going to put this now into the presentation. Opportunities, of course, they are there. Now, doesn't mean they're going to break a glass at every opportunity. The thing is, the glass will only break when the opportunity is there for it to occur. So in my festive seasons. Now, when you look at when each or why each failure happens, we can say, well, over that time, we're going to drop glasses out of our hands. So I've had 3 droppages in that period of time. Then occasionally a glass gets knocked. Then occasionally a glass gets stacked badly. Stack a glass and it gets cracked as it's stacked. And there's reasons, in this case it's on a tray, the tray got knocked and the glass falls off a tray. So we can begin looking at the reasons for our failures. So this curve, the curve that we came up with, 0.167 average across that family of 1 million glasses, that curve here is a result of the sum of all the failure causes. So in our machines, the curve for our machine is the sum of all the parts failure causes. So it says to me, gee, why, if we could actually do this, if we could actually reduce the failures, not have as many things go wrong, then my curve must come down. So by reducing that curve down, I have caused reliability. I have actually created a lower failure rate. They're breaking less often. And I've done that by removing the causes of failure. And when I remove the causes of failure, this gap here that would have been money lost and money spent on maintenance and money lost on breakdowns, it's not lost anymore. I have now got all this money that would have gone out as a cost in my back pocket as a profit. So equipment wellness, plant wellness is all about that. How do we make our plant so well, so healthy, and maintain that forevermore that we don't have so many failures? And if I can drive my failure rate down, which I can do by stopping the causes of my failure, then I will make money through making reliability. And that's the financial driver in plant wellness. We make money by not spending it because we save it because nothing goes wrong. We prevent the causes of failure. And to me as an engineer, the mathematics makes perfect sense. The logic behind getting money back by not spending it made a lot of sense to me. And so the challenge becomes, what are these causes? How do I stop them from happening? Please.
Is the ultimate goal for plant and equipment wellness zero failure rate? Is that, as opposed to some techniques which have a goal of 4.5 sigma, and then you can live with 3.4 defects per million opportunities, and if you ever get that, you're done?
Yes,
or,
yes.
Or do you always want to drive to zero?
In the end, it's a financial choice. A company will decide what risk they want to live with, and whatever number of failures that means, that's what they target. Me personally, I like to have no limits. I'm a great believer in the word excellence. Always driving towards a better outcome. Don't expect perfection. We are not a perfect species. We aren't going to get perfection, but the challenge of getting better and better is what's important. So I believe, I sort of, in the book I put it in the terms of no failures in the working life of the equipment. You know, so it means we have to maintain the machine. I'm not saying not maintain, I'm saying no failures in the working life. So if the working life is 10 years, then no failures for 10 years. If the life is a 25-year life, which the project guys would have decided back at the very beginning, we want this plant for 25 years, then I'm going to target for 25 years, no failures. Will I get it? Probably not early on. I'm going to work and develop my business and improve my processes towards that. But yeah, both ways are right. As a businessman, a certain value. Me as a person that likes the word excellence and what it means, I'm going to try for the best possible outcome. It's the same story. Every time I prevent a failure, it's profit. If I can drive this to zero, economically, makes a lot of sense. So the word economically is a big part of plant wellness. It has to be financially justifiable because there's other things I can do with my time and money and I put it towards where the best payoff is. But yeah, in the end, I would love to be able to say, at least during the service life of that machine, no zero failures as a strategy. Worst case would be whatever risk your company is willing to carry. So we'll talk about risk a little bit coming up because that's the very concept we have to begin to manage around. Now, of course, these curves apply to every single part. And every single part has many ways of failing. Now, here on the car tyre, I've only put down natural wear and puncturing, but there's other ways. There's misalignment, there's out of balance, there's a whole bunch of other things that can cause my tyre to fail. The point is the failure of my tyre is the sum of the failures of that lead to that final tyre loss. Same with the bearing. I might get a curve for all the bearings in my business or a bearing across its life, but that final curve is the sum of all the other failure causes. Misalignment, poor lubrication, wrong lubrication, dirt and contamination. So all these causes here, if I can remove each cause, then I won't have it creating the outage from a failed bearing. So I've got to find out what causes misalignment and stop it every single time. So I've got to understand where that can occur. How can this pump be misaligned? How can these shafts be misaligned? What are we doing in our company to make sure they are perfectly aligned or as close to perfection as we possibly can get? Same with lubrication. How do I know it's the right lubricant? How do I know the condition is right? So I've got to start defining parameters of excellence that deliver the results we're after. And that then becomes what we put into our strategies, our procedures, our training. And we bring everybody up to the level where they understand what is causing problems, what can cause them, and what they can do to prevent it. So yeah, we saw this before. We know why our parts fail. There is a full understanding, scientifically, engineering-wise. We have clear reasoning and clear examples of why things fail. Our machine fails because the parts fail. If I prevent the parts from failing, then my failure curve comes down. How do I prevent the parts from failing? Well, because we know the causes. Have known these for at least 25 years. There's nothing new here. So I want to build a process where each of these causes is discovered, is prevented, is put into our practices, and our people do the right practice. So our distribution of outcomes comes exactly to the requirement that gives us a long service life and no failures. So plant and equipment wellness is about creating this situation here, preventing things from failing. Because they're not failing, our machines aren't failing, reliability is high, uptime is high, and the machine doesn't cost as much, and it can produce more and make more output for the company. So all the things companies want, all the things that we as people in businesses want, we can achieve through reliability. Reliability will free up a lot of money, improve safety vastly, and all because we can control the situations that cause these things to break in the first place. This is an interesting one. This is actually a result of a company in Australia. One Steel is a steel mill. We don't have many left in Australia. There's a couple. One of them is the One Steel operation. And what they did was go back and have a look at all their work orders, maintenance work orders, for a period of time. And this is the pie chart that they put together. And what they found was that 48% of their maintenance was repeated every 3 months. In fact, 30% was repeated every month. So every month, the same things broke again and again and again. And after 3 months, half of the maintenance was repetitive maintenance. It got them to investigate why these things are happening. This company's been on a journey now, a reliability improvement journey now, for about 8 years. And in that 8 years, they've learnt a lot about why their plant is a problem for them. What they found is that if we want to have high reliability, there's a particular zone we have to be in. This curve here talks about what is an acceptable degree of perfection and what is unacceptable. What they found is that if we are not in this zone here, this particular area where there is no misalignment, no out of balance, if the vibration is not low, if the design loads are not as designed, if we have water and contamination in our oils, if we have high temperatures in our bearings where the clearances change, if we are this side of that line, where close enough or it's tolerable or it's acceptable, it's not. Once we are this side of that line, the reliability drops to fractions of the design life. It isn't until we cross that boundary and there is no misalignment, there is no out of balance, the total vibration is very low, the design loads are what they should be and where they should be, the oil and lubricant is in very good condition, the temperatures are controlled, so the interference fit of parts are as they should be in that 10 micron zone. Once we cross that boundary and we control the world our parts live in, our reliability jumps up to the full design. It's not a gradual jump, it's a step change. Massive step change. But we have to be in that zone. Nothing else but being in that zone gives us the reliability that we're after. Anything on that side, we never get the uptime, the low costs that are possible with high reliability. High reliability is this zone here.
Is a part of the problem that the company doesn't require the suppliers to meet any better standards. And so the suppliers are just giving them the minimum that they can get away with. And maybe if the company requested better tolerances or better overload, that the suppliers would actually give it to them.
Certainly, if the design is poor to start with, if it's the wrong design, if it's been engineered incorrectly for the situation, then you're going to get poor reliability. So definitely that design choice and the quality of that design and the quality of the build, major factors. Now, if you're a manufacturer and you have no idea that reliability comes from precision, you'll never ask for it. The thing is, once you know you've got to be in the zone and nothing else but that zone will do, you can go and ask for that. Can the supplier deliver it? I don't know. If they could deliver it, they might do it. What bothers me, it says to me that the manufacturer of machines don't understand this themselves. I'm buying machines brand new that are nowhere near this zone to start with. Brand new machines. The manufacturers around the world, few of them, I can't say everybody, but few of them understand this concept. There's only a very small tight zone and it has to be in that zone, and anything else, close enough is not close enough. It's going to be, it's a step change. It's fall off a cliff. It's like falling off a cliff. So in plant wellness, precision maintenance is about, that's the zone of precision. What is that zone? What are these numbers that ensure we're in that zone? Because I know once I'm in that zone, it will be right. Then I'm going to build the process, the business process that always drives us to this zone, because the message is very clear. If I'm in that zone, I will get reliability. I can create reliability intentionally, but I have to know those numbers. And my guys have to understand what those numbers mean, and my suppliers and manufacturers have to understand those numbers as well. So I might have to go back out and educate my suppliers and say, guys, here's the zone we want your machines for you to build to. And anything else less than that, go back to the shop floor and do it properly. So that's part of the solution for sure. That's what I'm saying. We've known these answers now for at least 25 years, yet it's not happening. So this connection between knowledge and practice in the real world, there's a misconnection, and we've got to make that connection as soon as possible, because that's going to make a big difference to all of us. Now this, as it says there, where do failures start? And bear in mind, a lot of these things I did for many, many years myself incorrectly. I was university trained. I'm a tradesman. I was put through trade school, full apprenticeship. And I was taught things that I simply followed throughout my whole career, until the day came when I was 49 and said, look, why isn't this working? Everyone else in the world is sent to do it this way, and I've been taught this way, and university tell me to do it this way. I've just been doing what I've been taught, except I keep getting failures. I can't get that failure rate down. So I began looking for other answers, and they're out there, because there are companies that do reliability very, very well, intentionally. DuPont's a classic. Toyota is another one. Many companies have solved these problems. So their answers are out there, just that I hadn't found those myself. So I began looking for those. And one of the things that you come across very quickly is variation. And variation leads to problems if the variation is uncontrolled. And what I've got here is 6 different ways to tighten fasteners. And here is the accuracy of each particular technique. So if I use operator judgment, which is muscular feel, the guy puts his wrench on there, I want to use a wrench, a ring spanner or a socket, puts it on there and he pulls it. And of course we feel the tension here. If I'm a big guy and I pull, or I'm a little guy and I pull, is that the same tension? Can't be. Yet we're both going to say from our muscular tension that, oh look, she's sweet. No, that is right. Boss, that is spot on, no troubles at all. But the big guy and the little guy can't be the same. So the process we've chosen of doing it with our muscles has huge variation, plus minus 35%. The small guy and the big guy will swear black and blue they've got it right. Because, the muscles tell them it's right, except they can't be right, it can't be the same. So the choice of my process defines the outcomes. In this case, if I have muscular feel, I must also accept, as part of that choice, there'll be broken fasteners and loose fasteners. And that will be the outcome always from that choice. It's a natural state of that process. So I say, too much variation, let me go to a torque wrench. Plus minus 25%. Better, but not fantastic. You can improve that if you do the right torque wrenching techniques, and there's particular methodologies to use to get that down to plus minus 15%. But you've got to do it a particular way and follow that way every single time. But nonetheless, if you have a torque wrench as your preferred way, then you will have occasionally snapped fasteners and loose fasteners, even though you're using a torque wrench. Then we go to turn of nut. Turn of nut is a technique where they pull the fastener up tight, as they call it, snug tight, then mark. They then mark where the fastener is, work out the angle it's got to go through, and rotate the fastener through that angle. And that angle of rotation then pulls the shank to the tension it requires. So it's not too bad, not a bad technique. Next one is load indicating washers. And load indicating washer is what it says. When the washer is squeezed to a certain point, a telltale evidence shows that it is now fully tensioned. And that is far more accurate. When I've seen these used in the mining industry in Australia, used them typically on vibrating screens with a lot of shaking of the fastener, when I've seen these used, the problem of tensioning goes away. So this says to me as an engineer, plus minus 10% is about where you want to be in accuracy to prevent these sort of problems. Further on down, we have fastener elongation. So the actual shank, as I tighten up the bolt or the nut, the shank actually grows. And I can measure that growth, and that growth represents the tension in the shank, and that is a very accurate process. So things like hydraulic nut tensioning would fit in this situation here. So we actually either micrometer the shaft, the shank, or these days ultrasonics. They shoot ultrasonics down, it'll bounce off the bottom, come back with a value of the length of that shank. So we can actually get a very high degree of accuracy. And the ones that is the ultimate is the strain gauge. We actually measure the microstructure growth. Very, very accurate, very expensive. Typically used, I guess, in space, in outer space equipment, and deep sea, where things go wrong, can't afford to go wrong down deep sea because it's so expensive to go and repair them. The whole point being is the process I choose delivers the distribution of outcomes of that process. Once I make the choice, that is it. That's what will happen. Now, what tricks us is this standard deviation. In muscular feel, this deviation is about plus minus 12, one standard deviation, plus minus 12%. So most of the times, using muscular feel will be okay. It will get away with it most of the times. But every now and again, we're going to get broken fasteners and loose fasteners because the strength here is over-tightened and here it's under-tightened. And that's the result of choosing that process. So my business, I've got to be very careful what process I choose, because the process delivers the outcomes. It isn't the people. It isn't the people in the process. It is the choice of the technique and the tool that delivers the outcome. So if I've got to have a process where I cannot allow my fasteners to be improperly fastened, they've got to be at the right tension and torque all the time, I can't use muscular feel. Muscular feel will guarantee failures every now and again. I've got to go down to something like turn of nut, load indicating washers. And if I don't choose those, I can never get those results, except by luck. Every now and again, mostly, what is it, 68% is in that zone there. So most times it's going to be fine. And that's the trick. It will look at that and say, well, that one's okay, no troubles, no troubles, no troubles. And so we'll think that works fine, except the outliers are the problems. And there are outliers built in to this as part of its use. As an engineer, I was taught, doing up things by hand is fine. As a tradesman, I was taught doing up things by hand is fine. Well, it is fine if you don't mind things being occasionally broken or occasionally loose. Now, if you can afford that risk in your company, you cannot afford this to happen every now and again, then you've got to change your process. If you can afford these situations to occur every now and again, then leave it as it is. Don't mind things coming loose because it's no big deal. But if it is a big deal, this comes loose and something breaks and it's down for a couple of days or a couple of months, then you can't use this process because you can't control it. And that's the bit that took me a long time to understand. It's a process issue. It isn't a people issue. If the people don't know these techniques, then I've got to teach them. But once they know the techniques, now I have a control. They know what they're doing, and we can put protection into how they use those. All right, this is a machine. This happens to be an engine block, and it's made of parts. Some of these parts are high risk. For example, anything that moves. So my pulley there, another pulley over here, my valves, my pistons, anything that moves in a machine because it's working, it's at a risk of stress. So I can take parts drawing and begin to say, okay, where are the high risk items in my parts? Which ones are the ones that are likely to give us a problem? So I can now take my parts list and put on my stress manager's hat and say, okay, which of these parts are going to wear out from use? In which case, if they're going to wear out from use, I'm going to inspect them on a regular basis to see how quickly they're wearing and track that and trend it and monitor that. What parts will actually degrade from use? What parts are intentionally going to fail by their service? Here we go, oil filter. That filter will degrade intentionally by use. And there's a fuel filter in there as well. So any parts that by their use will be contaminated and will degrade on purpose, it's designed that way, well, I want to renew those at a particular frequency. which parts are going to fail from stress? And these are going to be the parts that see high temperature, high loads, high working operating conditions. If I can identify those off the drawing board, then I know I'm going to have to do a couple of things there. One is to monitor their condition, keep an eye on how much stress they're accumulating, and more importantly is to not let them get stressed, because stress is the killer. Some operating practices, I'm going to have precision operation. I'm going to train my guys how to operate that machine perfectly, because I know from the design engineering what its operating zone is. So I'm going to teach my guys, I'm going to design that process of operation, written it right down, like a movie script, right down to the detail of exactly what to do when and how to do it, and train my guys to this, because I know if I can control stress, I'm going to control reliability. And same with precision maintenance. I'm going to make sure the machine goes back in prime condition, everything's spot on. Because I know where the trouble's going to be. From my experience as an engineer, as a designer, as an operator of these machines, I understand where the troubles will be. The big one, which is the one we're going to have to front as an ongoing issue, is error, installation error, human error. How many of these parts can be put back incorrectly? Because if they can be put back incorrectly, and because they go back in incorrectly, it leads to a breakdown, I want to know that now. So when I build my manuals and write the procedures, I'm going to write exactly what to do properly. Because I have no choice. I've got to be in that zone. I've got to be in that zone all the time, from the day it's brand new to the day it retires in 25 years' time. And I've got to build the process to be in that zone all its life. If I can do that, then I am controlling the scenario of this machine's reliability. And I can do that off the drawing board, off the parts list, because I can find those risk scenarios and put into place some protection against those risks. So when it comes to wellness, what will make these parts well, and how do I keep them well all the time? So yeah, reliability is something that is creatable. We can actually make the reliability we want. So when I say failure-free for operating life, I'm sure it's possible. Sure it can be done. Whether it's worth it financially, well, the numbers will tell. Not hard to work it out. The numbers will tell. A spreadsheet will tell us the smart things to do. But certainly the answers are all there, have been there for a long time, they're just not in use.